Large furniture items typically limit the amount of usable space in a room, especially when they only have one function. Increasing the amount of uses a piece of furniture has can improve the amount of usable space in a room. For our project, we are combining the functionality of an ottoman with that of a coffee table. This provides much needed space saving for individuals who have small apartments or for students who live in dormitories. The functionality of our project is simple. You remove both sections of the tabletop, slide them into place, and press down. Then the middle section rises.
Here is how it works. The side tables are shifted from the top of the ottoman and placed on the base sides, causing it to push the actuator down. As the actuator is pushed down, it makes the lever arm pivot and changes the scissor link's position. When the scissor link moves, it adjusts the height of the middle tabletop, causing it to go from being hidden within the ottoman to completing the coffee table. We analyzed two 3-bar crank sliders. The first crank slider can be seen as when the scissor links are pushing against the middle tabletop, driving it up and down. The second crank slider is the lever arm pushing against the scissor link. Using the vector loop method, we derive the position of middle tabletop C with respect to the change in angle created by the scissor link to theta 2. Using scaled heights, we found that we wanted our heights to be 1.8 with an output angle of 68.4 degrees raised to 2.6 with an output angle of 12.4 degrees, meaning the scissor link must be able to rotate 56 degrees. Proving the design is feasible.
For our force analysis, we analyzed the two 4-bar linkages in our project. The first is a crank slider mechanism found in the middle of the table. The second is an inverted crank slider mechanism found to the sides of the table. Here is a simplified drawing of what the crank slider mechanism looks like in the project. For our analysis, we'll only need to show the free body diagrams of the left half, which includes links 1 through 4. Here is a drawing of the inverted crank slider mechanism in the project. As a pin is fixed near the center of link 7, a downward force caused by an actuator creates a moment about that pin. The other end of link 7 pushes link 2 upwards via a connecting rod. In the free body diagram, link 2 has another force acting on it, denoted as F rod. And here are the equations of motion for both the crank slider and inverted crank slider mechanisms.
Because the connecting rod is the main interface between the applied downward force and the upward motion of the tabletop, it is our main concern for stress analysis. In our design, we specify use of aluminum as the connecting rod's material, which has a yield strength and shear of 30,000 psi. The connecting rod is simplified in this analysis to be a circular beam experiencing a pure bending scenario as shown. The 4 concentrated loads represent each interaction with both the lever links and the scissor links. The equations used for this analysis are bending stress, transverse shear stress, von Mises stress, and a safety factor for failure and shear. The given yield strength and shear results in a safety factor of 17, which seems slightly high but will provide a functional prototype. Optimized prototypes may be achieved through smaller dimensions or use of a different material.
Here is the mechanism again in motion.